relies on a straightforward premise: feeding a system labeled historical data to teach it how to predict future outcomes. But the moment you build one of these systems, the data forces a structural divide. If your goal is to sort discrete items into clear buckets, like identifying whether an image is a dog or a cat, you use classification. But if you need to map a continuous numerical spectrum, you use regression. This chart highlights the geometric difference between the two. Classification groups data into distinct, bounded zones. Regression maps a continuous relationship between variables to calculate an exact value. A regression algorithm doesn't ask what category an object belongs to. It calculates precisely how much sales volume a specific store will see next March, based on historical patterns. To accurately predict these real-world numbers, we have to build mathematical architectures capable of adapting to highly complex, multidimensional realities. The engineering problem we face is variance. Reality is messy, and human behavior, markets, and physical systems rarely follow perfect, uniform rules. To understand how an algorithm makes sense of this variance, we have to strip predictive modeling down to its mathematical foundation. We will build these regression architectures from the ground up. We begin with a simple two-dimensional line, extrude that line into higher dimensional space, and finally, warp the geometry to fit nonlinear systems. Transforming a raw dataset into an accurate forecast is an exercise in matching the architecture of your equation to the physical topology of your data. The simplest baseline architecture is linear regression. This graph maps a single independent input against a single dependent output. For instance, comparing the number of hours a student studies against the marks they score on a test. The algorithm calculates the mathematical average of these points and draws a single straight line through the center of mass. This line is defined by the equation y equals mx plus c. Y is the predicted test score, x is the input hours, m dictates the slope or angle of our prediction, and c acts as the intercept, setting the baseline value if the student studies 0 hours. This structure assumes a strictly proportional relationship. If the input increases, the output increases at a constant, uniform rate. The mathematical flaw here is isolation. A student's test score is influenced by sleep, attendance, and health, not just the raw hours spent reading. A strict two-dimensional line cannot map a multifaceted outcome. To capture that complexity, we have to scale our geometry. When a single variable is insufficient, we upgrade the architecture to multiple linear regression. We pull the model out of a flat plane and expand it into a three-dimensional feature space. The equation scales to match. Instead of a single x, we now have x1, x2, and so on, with each input assigned its own specific weight, represented by the a coefficients. The predictive geometry is no longer a rigid line. It becomes a hyperplane, a flat surface slicing through the suspended data points to establish a multidimensional average. Consider predicting the price of real estate. The rent of an apartment depends on a matrix of distinct inputs: which floor it is on, the total square footage, and the exact number of bedrooms. Each of these inputs exerts its own mathematical gravity, pulling the final predicted rent up or down along the surface of the hyperplane. By processing multiple vectors simultaneously, this architecture accurately maps multidimensional linear relationships. There is a persistent engineering assumption that feeding an algorithm a wider variety of data columns will automatically yield a more accurate prediction. This ignores the destructive nature of noise. Noise refers to irrelevant data inputs that have no causal correlation to the target output. If you are predicting a student's test score, including their diet and sleep schedule is highly relevant. But feeding the model data on the type of house they live in or their method of commuting introduces mathematical deadweight. When you force an algorithm to process this irrelevant noise, the architecture collapses. The hyperplane contorts itself, warping and folding erratically to intersect with random data points that carry no actual predictive value. This failure state is known as overfitting. An overfit model has successfully memorized the chaotic noise of its historical training data, which completely ruins its ability to accurately predict future, unseen realities. Expanding the feature space is a mathematical liability unless every single variable directly influences the core relationship. Even a perfectly calibrated hyperplane relies on a critical assumption that variables scale in straight, continuous directions. Population growth cycles, seasonal market trends, and viral adoption rates do not move in straight lines. They oscillate, spike exponentially, and decay. This graph illustrates the failure of a linear model against nonlinear data. If you plot seasonal retail sales, the data naturally forms a curve. Forcing a rigid, straight line through this cluster misses almost every target. The vertical distance between our straight prediction and the actual clustered reality represents a massive margin of error. To solve for this variance, we implement polynomial regression. We altered the physical geometry of our prediction by introducing exponential powers into the base equation, adding an x squared or an x cubed term to the features. The math adapts. The predictive line loses its stiffness. It bends and threads directly through the oscillating data, drastically reducing those error gaps. Polynomial architectures allow us to map the actual curvature of a volatile system, calculating accurate predictions where simple proportional models break entirely. Regression provides the fundamental mathematical engine for predicting continuous numerical values, but no single equation applies to every dataset. This dashboard compares the three distinct geometries we've built. When new, unseen data points are introduced to a correctly calibrated model, they track perfectly along the predicted path. A single dominant variable dictates the simplicity of a straight line. A matrix of interacting features requires the high-dimensional space of a hyperplane, and a system governed by oscillation demands the fluid curves of polynomial powers. Building an effective machine learning pipeline is an exercise in restraint. You select the exact mathematical architecture that reflects the physical dimensionality of your system, ensuring you capture the signal while strictly rejecting the noise.